So I am back. Let's see. I'm back and we're continuing volume 1 of this DOE manual for this thermodynamics class. And where we last left off, we were talking about, thermodynamic like properties of processes, thermodynamic properties, and the way we like to think about systems. And so now we're going to talk about change of phase. So the phase change of a material in a system is important to the study of thermodynamics. It's essential to understand the difference between the solid and liquid, or between the liquid and the vapor, and how this is used to enhance like the performance of a system. So it's important to understand phase. Now, there are certain gas laws where we think about phase, and there are certain properties of solutions where we like to think about phase. And so, like I said, knowledge comes from the top down, and sometimes the way that we've worked in thermodynamics to understand phase changes has impacted people's daily life. So we're going to distinguish between intensive and extensive properties, and then we're going to talk about saturation. We're going to talk about subcooled liquids, superheated vapor, critical points, on a graph, triple points on a graph, the vapor pressure curve, quality, and moisture content. And then we're going to describe processes. And I think we talked about this a little bit before, sublimation, vaporization, condensation, and fusion. So these classification of properties, we talked about this earlier, and these properties are classified as either intensive or extensive. Remember when we talked about intensive, they were independent of mass. We talked about like temperature, pressure, density, specific volume, how those were intensive properties. And then extensive, they're directly related to the amount of mass present. So properties such as, like I said, pressure, density, those are intensive, and volume and then mass are extensive properties. And these extensive properties may become intensive by dividing the property by the total mass. So they're trying to give you a way mathematically that you can look at this extensive property as an intensive property. Total volume, which is an extensive property, can be changed to a specific volume, which is an intensive property, by dividing by dividing it by the mass of the system. Okay. So any specific property, specific volume, enthalpy, specific entropy, is an intensive property. It is an intensive property. So specific properties are intensive properties. The use of intensive and extensive is demonstrated by the following. So they want you to consider like a system. So 1 pound mass of water contained in a piston cylinder arrangement. This is in this figure. Let's see if I can. No, I can't capture it at the same time. The piston and weight maintain a pressure of 14.7 psi. I like to use the piston sometimes to talk about Boyle's law, but also I like to use the piston to talk about the relationship between weight, mass, pressure, and volume. And what you see is that the initial temperature is 60. As the heat is transferred to the water, the temperature increases. The specific volume starts to increase, and the pressure remains constant. Okay. When the temperature reaches 212, additional heat transfer results in this change phase. So you go from the liquid starts to boil. Okay, and so when the liquid boils, you have a liquid and a gas phase. Okay, so some of the liquid becomes vapor, and both the temperature and the pressure remain constant. All right, because we're inside of this piston. The way we used to like represent pistons was to use like a syringe. That's the way we like to think about a piston. So if you want to think about a piston that way, you can understand how temperature and pressure can remain constant. Okay. But the specific volume increases considerably. And when the last drop of liquid is vaporized further, transfer of heat results in an increase in both temperature and specific volume. Temperature and specific volume. Okay. So in the example mentioned, talking about the piston, temperature and pressure are intensive, and they do not depend on the amount of mass present. By examining the specific volume of an intensive property of water in the piston instead of the volume, which is the extensive property, we can talk about how the water inside of a piston changes. So volume by itself tells us nothing about the water in the piston. However, knowing the specific volume can tell you if the water is a liquid or if it's steam. Why? Because liquids, if you put a liquid inside of a cylinder, you can tell what the volume is. If you put a gas inside of the cylinder, you have to look at the volume of the entire cylinder to tell you how much volume that gas is, because those gases will occupy the space of the, that they're put in. So they'll basically be the volume of the container. Okay. A liquid, you pour it in a cylinder, look at the meniscus, you get the volume. You put a gas inside something, do you have a meniscus to look at? No, you do not. All you have is the container and how big the container is. So it's customary to define some intensive properties associated with extensive properties. For example, I think we just talked about that. Volume per unit mass is called specific volume. I think we covered this equation in earlier discussions, where lowercase v is equal to v over m. And internal energy per unit mass is called specific internal energy. We covered this concept before. So lowercase u is equal to u over m. Intensive properties, they're useful because they cannot be tabulated or graphed without reference to the amount of the material that you are studying. Okay, so intensive properties are still useful because you can't graph them or calculate them without reference to the amount of material in the study. And so, of course, in all of these, you see this is per unit mass. Okay, and so they're saying that you cannot graph the two terms that I showed you that are intensive properties without understanding the mass. We covered this part about the piston. So here you're looking at water, and in figure A, and this is before you transfer the heat. Okay, so you've compressed this liquid water, right? And you haven't put the heat there. Then this vapor pressure. So once you transfer the heat and the water starts to boil, then of course the gas exerts pressure and pushes this piston up. Okay, the gas exerts pressure and pushes this piston up. All right, and here all of this water is converted to water vapor, and the piston is pushed up even further. All right, so that is the example that they were giving you earlier. So the term saturation define. Okay, so this is a pressure temperature graph here that you see. So the term saturation defines a condition in which the mixture of vapor and liquid can exist together at a given temperature and pressure. The temperature at which vaporization or boiling starts to occur for a given pressure is called the saturation temperature or the boiling point. Okay, so they're using these two terms interchangeably. The pressure at which vaporization or boiling starts to occur at a given temperature is called the saturation pressure. Okay. So for water, 212 Fahrenheit, the saturation pressure is 14.1 psi. For water at 14.7 psi, the saturation temperature is 212 Fahrenheit. So for a pure substance, there is a definite relationship between saturation pressure and saturation temperature. So we're talking about a pure substance, okay? So if the substance isn't pure, there are other interactions molecularly that you have to account for. So we're talking about a pure substance. The higher the pressure, the higher the temperature. So I'm just going to use my mouse. So if you look at this graph, or orient yourself to this graph that's on the right side there. On this y-axis, you have pressure. Along this x-axis, you have temperature. And you can see based on the way that this curve is that as you increase pressure, you increase the temperature. So this is increasing from the origin out in temperature. And as you go up for pressure, it's increasing from the origin up. And that's what they're trying to show you, is that this is a positive type of graph. So this is just showing you that as you increase the pressure, you increase the temperature and vice versa. So the graphical representation of this relationship between temperature and pressure at saturated conditions is called the vapor pressure curve. Okay, so this is called a vapor pressure curve. So, yeah. So a typical vapor pressure curve is shown here. And like I said, this will represent like a positive slope. So as X is increasing, Y is increasing. So as pressure is increasing, temperature is increasing, and vice versa. The vapor liquid mixture is at saturation when the conditions of pressure and temperature fall on this curve. So they're saying that when those points fall on this line, and as you increase the pressure, as you increase the temperature, the pressure is going up, then you have a mixture that is saturated. You have a mixture that is saturated. So saturated and subcooled liquids, and they're thinking about solutions again, or they're thinking about substances. If a substance exists as a liquid at the saturation temperature and pressure, is called a saturated liquid. Okay, water is just water. Water is just water. And it's 100% water. So water is just water, and it's 100% water. If the temperature of the liquid is lower than the saturation temperature for an existing pressure, is called a subcooled liquid, implying that the temperature is lower than that at the saturated temperature for this given pressure. So it's subcooled. This is something that I don't know if you guys have seen this before, because sometimes on YouTube they have these cool videos, and they will subcool some water and then pour it out and let it turn into ice. First they'll subcool it and it's still like kind of liquidy, and then they will pour it out and it'll just turn it into an ice structure. So that's like, okay, I've got this below the freezing point. Then when I pour it out, then I know that this water is below the freezing point because it turns into ice. Okay. So if a substance exists as a liquid at the saturation temperature and pressure, like I said, it is a saturated liquid. If you don't have a point on this line and you cool this past the freezing point, then you have a subcooled liquid. Okay, a compressed liquid implies that the pressure is greater than the saturation pressure at a given temperature. So I guess the best example I could give about that is soda. That's the only thing I can think about, something compressed that has the sort of pressure to it. That's not the example that they're thinking about here, but if I think about like pushing CO2 inside of a liquid, and the best thing I can think about is soda. And that's something that you have to apply pressure to push that gas into that liquid. That's the only thing I can think of. So applying this sort of pressure, it gives you a type of compressed liquid. It gives you a type of compressed liquid. So both terms have the same meaning. So either term can be used, and that's kind of like the way I like to think about it. So they're saying a subcooled liquid is a compressed liquid, because you're taking these water molecules, if you subcool it, and you're forcing them to be close together. And then when you've seen people pour it out, it turns into this ice structure, because the water molecules are close enough that they give you that crystalline structure that you get with ice. That's the only way that I can think about that example. And so you're thinking about the pressure pushing these molecules in so that they order and arrange themselves, just like what happens in an ice cube. Quality is when a substance exists as part liquid and part vapor at saturation conditions. And quality, X, is defined as the ratio of the mass of the vapor to the total mass of both vapor and liquid. Thus, if the mass of the vapor is 0.2 pounds per mass, the mass of the liquid is 0.8 pounds per mass. The quantity is either 0.2 or 20%. Okay, so they just took that and multiplied it by 100 and gave you a percent. And quality is an intensive property. So you need to understand that quality is an intensive property. So the area under a bell-shaped curve on figure 6 shows the region in which quality is important. The area under the curve shows you where quality is important. And just in general, when we think about area under the curve, like for me, it helps me when I'm doing any sort of like spectroscopy. I think about area under the curve. So I can try to figure out, I know the area under curve is normally volume, but area under the curve helps me figure out concentration too. Like when I can't figure it out any other way, I know that I can go to area under the curve and figure out concentration. So area under the curve is normally volume, especially if you're talking about Boyle's law. Okay, so here, let's go back to this equation. So the area under a bell-shaped curve in figure 6 shows the region in which quality is important. Quality, remember we said that was X, and X is equal to the mass of vapor over the mass of the liquid plus the mass of vapor. Okay. So the area under this curve shows you, this is the bell-shaped curve. Okay. This is the bell-shaped curve. And so this area under this curve is where quality is important. Okay, so I'll finish up this, and then we'll finish our notes. So the moisture content of a substance is the opposite of its quality. Moisture is defined as the ratio of mass of a liquid to the total mass of both the liquid and the vapor. Okay, and that's what you see in this equation here. All right, moisture is equal to M of liquid over M of liquid plus M of vapor. That's what you see here. So the moisture of a mixture in the previous paragraph is either 0.8 or 80%. Okay. And so this equation shows you the relationship between quality and moisture, the second one. So moisture is equal to 1 minus X. And so they're using X to talk about quality. So try to keep those straight, because earlier they showed you Z. Z was height, H was height. Here we have X, and you know, a lot of people use X as default, but in this case, they're trying to show the relationship between moisture and quality. So try to keep that straight. If a substance is entirely vapor at saturation temperature, it's called saturated vapor. So we're talking about saturated and superheated vapors. Okay, sometimes the term dry saturated vapor is used to emphasize that the quality is 100%. Dry saturated vapor, quality is 100%. When a vapor is at a temperature greater than the saturation temperature, it's said to exist as a superheated vapor. The pressure and temperature of a superheated vapor are independent properties. And since the temperature increases while the pressure remains constant, okay, since the temperature may increase while the pressure remains constant. And they're making the argument in your book that gases are superheated vapors. They're making the argument that gases are superheated vapors. Okay. So here you're looking at a temperature volume diagram. And so on your y-axis, if you orient yourself, there's temperature. On your x-axis, this volume. Of course, as you go up, temperature increases. As you go from left to right, volume increases. Okay, and this is figure 7. And they're looking at the constant pressure line that represents the states through which water of the previous discussion passes as it's heated from initial state at 14 psi at 60 degrees Fahrenheit. I think you guys have seen this before, because this is the temperature that engineers use when they start talking about STP. Okay, this is the temperature that they use when you start talking about STP. Okay, so that's not the way a chemist thinks about STP, but that's the way they think about it. Okay. For us, it's like 25 degrees centigrade, 1 atmosphere. Right. For this, you're using 14.7 psi and 60 degrees Fahrenheit. So state A represents the initial state. State B represents the start of the saturated line. So where is state A? Mm-hmm.
Going down at the bottom, right, where it says PM, IEM.
Mm-hmm. Yeah. What in the world? Okay. So therefore, line AB represents the process which a liquid is heated from initial temperature to saturation temperature. So I'm trying to get used to how engineers think about this. So where is A at? let's see,
Yeah,
A,
they use
B.
that to very bottom, the PMIEA, I mean, at the very bottom.
Yeah, hold on. I'm trying to think about how. So. Stuff my slide. So in this part right here, they're saying that the temperature is going up. Temperature is actually increasing. Here, the temperature is remaining the same. Remember, I was telling you guys about latent heat earlier, the phase change. So theirs just looks a little bit different from mine because they have all these different pressures here. They have all these. Okay. So their standard pressure, they're showing you, for example, if you have a liquid going to a vapor, at first you're going to have to heat the water, then it's going to change from liquid to gas, and then you can heat the gas. That's what they're trying to show you. Okay. And so that flat surface there on graphs that I would have seen is like latent heat. That's the simplest way I can think about
Can I ask you a question? But I mean, it's related kind of, but sort of not. But you was talking about the super cool liquids a while ago and how, people would do experiments with the super cool liquid and then pour it out and it hit the surface and it turn to ice. Is that what happened with freezing rain? Cause it's like super cool, like further up in the atmosphere, and
then when it hits down here and the
it
pressure
freezes.
changes, then it crystallizes.
Yeah.
Yeah.
Okay.
Yeah.
Okay.
So it starts out as a liquid, and then when it hits different pressures, then of course, yeah. So that's what they're doing. Like they're able to start it out, cooling it. It's in the same container, and that container just has one pressure. And then what they like to do is pour it out so they can change the pressure, or they can expose it to a different pressure. And then that's how they are able to pour it out, and it just makes this mountain of ice. So point C is at the vapor state. Line BC is constant temperature pressure process changing from the liquid to the vapor phase. Line CD represents the process in which steam is superheated at a constant pressure, and temperature and volume both increase during that process. So the way that they have, am I looking at it right? Make sure. Yeah. So the way that they've looked at it, for us, we would have gone ahead and made something that looks like stair steps, and every part of this stair step would have information for every phase and every change of phase. For this particular graph, each of the different lines are at different pressures, and then they're showing you times where this solid, liquid, and gas are heated, and times where they are changing phase. So their diagram looks very different from what you would see in a typical chemistry textbook. So Now we're looking at a process that takes place at a pressure of 100 psi. So go back to this, they're going back to this line here. So they're going from here up and then over. Okay. That's the way you need to think of those, because like I said, that's not how a chemist typically thinks about those stair steps that talk about latent heat changing in phase, and then that Q is equal to MC delta T. We just plotted quite different. So point E represents the initial state. The specific volume being slightly less than 14 psi at 60 degrees Fahrenheit. Vaporization, it begins at point F, where the temperature is 327.8 Fahrenheit, and point G is the saturated state, and line GH is the constant pressure process in which the steam is superheated. Okay, so like I said, the way that they do their graphs is quite different than the way that a chemist would do this graph. So this is definitely engineer, the way that an engineer looks at the same concept. So in a similar manner, constant pressure of 1,000 psi, and they're going to right here. Okay, so they're going this line and then over it. Is represented by line IJKL, and the saturated temperature is 544.6, and this is not so you would actually go over this way, and so they're telling you what these values are. It's not like you can look on the graph and extrapolate and see 544.6 degrees Fahrenheit. So the critical point is the pressure of 302.06.2 psi. So some of these values, like, you need to know them. Some of these values, like, you need to know them. So you need to know the pressure for your critical point, stuff like that. So if you see values written throughout here, you need to know them. Okay. It's not like they won't put them in the problems when they work them, but just keep this under your hat so that if you see it again in a problem, you understand where this comes from. So at pressure of 3206 psi, this is it. You see this line right here? Okay. It goes up, then over like this. Okay. This is represented by line M and O. There is no constant temperature vaporization process. Rather, at point N, there's a point of inflection. Okay, and so for us, when we think about like derivatives and calculus, then we start talking about points of inflection, but it's really like where the graph like curves in a different way. So let's say the graph, oopsie. Yeah, so in calculus, then we start talking about derivatives. We start talking about derivatives, then we start talking about points of inflection. Oop. And so if you look at this graph, it's curving this way. Then when it gets right here, it starts to curve up this way. Okay, so what's going on in here is a point of inflection. This is the point in which the graph curves up this way. Okay, so first it's curving like this, and then it flips and goes this way. Okay, so that point right in here is the point of inflection. This is the point where the graph changes direction, and this is you know, just a concept we talk about in calculus. So all you need to know is just a point in which the graph changes direction. If this graph wouldn't have changed direction, then you know, you would have seen like it curved, you know, it curved down this way or something. Okay. If it was going to keep doing what it did, it might go straight or curve down this way. It's not going to go up like this. Okay. That's a point of inflection. Missing something. Yeah. Point of inflection. And at that point, the slope is 0. So at that point right here where the graph changes direction, the slope is 0. Okay. At that point right here, where my hand is touching my arm, where the graph starts to change direction, that slope is 0. And this is called the critical point. Normally for us, we actually, you know, when I used to be in industry, we used to subtract every step from the step before it, see where we had the biggest like value change, and we would know that is the point of inflection. So if I would do a certain titration with like a certain type of it's called a potentiometric titration. And so if I were to use that, it kind of looks like a pH meter. And if I were to use that to do it, then I look at the point where I have this biggest change in line. And that's how I know what the point of inflection is. Okay. And so, like I said, that's called the critical point. And then the critical, just a moment. So, like I was saying, this critical point is, you know, this point where you have this inflection. And a point of inflection, the way we like to think about it in calculus, is the point in which the graph changes direction. And that point where the graph changes direction, the slope is 0. Okay. Fusion, if we think about that piston cylinder in the earlier figure 4 or the early example, suppose that it had like 1 pound per mass of ice at 0 degrees Fahrenheit, okay, and 14 psi. So when the heat is transferred to the ice, the pressure remains constant, the specific volume increases, and the temperature increases until it reaches 32 Fahrenheit. And that's the point, that's the melting point for the ice, okay? So that is the melting point for the ice. So in this state, ice is what you're calling a saturated solid, okay? So it's all H2O. It's a saturated solid. It's all H2O. For most substances, the specific volume increases during this melting process. Okay, so if you melt some ice, they're saying that volume normally in the real world, that specific volume does increase. Okay, but for water, the specific volume of the liquid is less than the specific volume of a solid. That's why whenever you freeze water, you get expansion. So if you were to take a soda or something like that inside of the freezer, it would explode. So this is saying that the volume is going to go up when you think about water going from a liquid to a solid. Okay, this is just saying, it's just talking about how that volume increases. Okay, so whenever you freeze something, it expands. And we talked about why a long time ago. So also, this causes ice to float on water. This is what causes ice to float on water. So when all the ice is melted, any further heat transfer causes an increase in temperature of that particular liquid. So if it keeps melting, then the liquid is just going to get warmer. Okay. So as it goes past that latent phase and it keeps melting, or the part this liquid keeps increasing in amount of liquid there, then the temperature is going to go up. The process of melting is also called fusion. And so the heat that's added to change that phase from solid to liquid or from ice to liquid is called the latent heat of fusion. You know, this is the point where the temperature is not changing because the phase is changing. Sublimation, if you have initial pressure of ice at 0 degrees Fahrenheit and 0.0505 psi, heat transfer to the ice results in an increase in temperature to 20 degrees Fahrenheit. And at this point, however, the ice passes directly from solid phase to vapor phase, and it's called sublimation. And like I said, the way you can think about or visualize sublimation is like if you have some dry ice. It doesn't have liquid phase, it goes straight from the cubes to this white looking smoke, okay? And that's another way to think about sublimation. Sublimation is a specific term that's used for cases in which the transition from the solid phase to the vapor phase occurs directly without passing through a liquid phase. So again, dry ice, start with the cubes, and then you get the white smoke. Okay, so further heat transfer will result in superheating the vapor. So if you keep putting heat to that dry ice, you're just going to get more smoke or warmer smoke. Let's just say that you just get warmer smoke. Triple point is we're looking at the initial pressure of ice as 0.08854 psi. And again, this is a result of heat transfer. The temperature increases to 32 degrees Fahrenheit. And at this point, the further heat transfer may result in some of the ice becoming vapor and some becoming liquid. So it's a triple point because all the phases are there and they may be at equilibrium. That's why it's called a triple point. So it's not a critical point like that inflection point. This is that one point where all the phases are right there. It's that one point where all the phases are right there in equilibrium. So you can see the vapor, you can see the liquid, you can see the solid. So let's see their interesting diagram. Okay, so turn to this, right? So this right here is a triple point. And at this point, there's equilibrium between the solid phase, between the vapor phase, and the liquid phase. Okay, there's equilibrium between all of the phases. And this is the critical point here. They're trying to show you that this triple point and critical point are different. And this is the point in which the slope changes or the line changes the direction that it goes into. Okay, this is the point where the line changes direction that it goes into. Okay, here's your fusion line, latent heat of fusion. Here's your vaporization line. And here is your sublimation line. Now at your sublimation line, you see you're going from, you don't have any liquid phase here as part of this graph. You go straight from solid phase to vapor phase. It's your sublimation line. Fusion line, you go from solid to a liquid. In vaporization, you go from a liquid to a gas, or a liquid to a vapor. Okay. Let's see how they describe it. So finally, you have to consider the initial pressure of 0.08854 psi. Again, as a result of heat transfer, the temperature will increase until it reaches 32 degrees Fahrenheit. And at that point, further heat transfer, like I said, could result in ice becoming a vapor and some becoming liquid, because it is possible to have all three phases in equilibrium, and that's called the triple point. So in figure 8, this a pressure temperature diagram for water. And it shows how the solid, liquid, and vapor phases can exist and be in equilibrium with each other. And then, of course, I showed you the sublimation line. I showed you the fusion line. And I showed you the vaporization line. And the phases that are along that line. So the only point at which all three phases exist in equilibrium is the triple point, and the temperature and pressure for the triple point of water at 32 are 32.02 degrees Fahrenheit, and the pressure is 0.08865 psi. So if you use those points, you can find the triple point. The vaporization line ends at the critical point. Okay, the vaporization line for this water graph that's in the aforementioned figure ends at the critical point. And so that's why they're showing you that there's a difference between a triple point and a critical point. Okay, and so we already covered this graph. Condensation, this is where we've discussed, this is the point where heat is removed and the opposite processes occur, condensation. So instead of making a gas, you're cooling or removing heat and you're making a liquid. Okay, so we call it condensation. So that's the reverse of the processes on this graph. Oops. Yeah. So here's your vaporization line. Normally you'll go from liquid to a vapor if you're adding heat. If you're losing heat in this vapor phase, you go from vapor to the liquid phase, and that process is called condensation. So as previously described, the heat addition at constant pressure to a saturated liquid will cause the liquid to evaporate. Okay, so it will change from liquid to vapor. If the heat is removed at a constant pressure from a saturated vapor, then condensation occurs. Okay, and similarly, freezing is the opposite of melting and fusion. So, pictures. Okay. So this fusion line, if you go from solid to liquid, this is fusion, but this is you going from liquid to solid, which is freezing. Okay, which is freezing. So freezing is the opposite of melting and fusion, and sublimation also has an opposite process where gas goes directly to solid. The process is not normally referred to with a unique term. And then, of course, you'll go through the summary, and any formulas that you need, you'll go use those formulas. You'll add them. Any constants that you saw, please make sure you notate those. Because there's just a lot when it comes to how an engineer plots these same concepts.